talk about the next section today, which is going to be over average rate of a change of functions. We've already talked about how to do net change, right? We did net change in a previous section. How did we define net change again? So if we had the net change of a function f of x from x equal to c to x equal to d, what was that equal to? It was not quite d minus c, but well, it's change in the function. So I don't always want to do d minus c because that's the change in the inputs. I want the change in the outputs. How do I get the outputs? Yeah, f of d minus f of c, right? That's net change. Okay. So, for example, and I think I kind of give an example like this when we talked about net change. If you start a trip 10 miles from here and you end up 50 miles from here, how far did you go? 40 miles, right? Or say I started from here and I traveled 300 miles. The net change of that would be 300, right? Okay. So that's just net change, just where you ended up minus where you started. Okay. So again, we think about this is where we started. This is where we ended up. That's what we subtracted the two. Let's go a little bit further with this concept. So again, if I say if you traveled 300 miles and it took you 5 hours to do it, what was your average speed on that trip? 60 miles per hour. You divide, right? Okay. So if we want to do average rate of change for a function, we're going to do exactly the same kind of concept. So average rate of change of a function from x equal to c to x equal to d. We're still going to do our net change. How far did you go? That's f of d minus f of c. We're going to divide that by how long did it take. We'll divide by the d minus the c. So thinking about what the denominator will look like, if you started an hour from now, and it took you until 6 hours from now to do that 300-mile trip, the 6 minus the 1 would give you that 5 hours that it took. So again, the top is basically how far did you go? The bottom is how long did it take? That's average rate of change. Okay. All right, so looking at this first example that we have, we've got a table of values. The year is the input. The population is the output. So the first part asks you what's the average rate of change between 2008 and 2012. Again, if we're just thinking about functions, okay, just writing what the formula would look like, the average rate of change would be the population in 2012 minus the population in 2008 over 2012 minus 2008. That would be the formula, right? Where you started, 2008, where you ended up, 2012. So that's how long it took. This is how far you went, right? How much the population changed. We should be able to read those populations off the table. What was the population in 2012? Yep, 6375. Population in 2008 is 4869. And then if I subtract in the denominator, we get 4. It's 4 years from 2008 to 2012. And what do you get when you simplify that? $376.5, is that what you said? Okay. All right, so now let's think about what the units on this would be. the numerator, the top of your fraction, is number of people, right? What's the denominator? Years, right? So people per year, right? So that's the population. Average rate of change is 376.5 people per year. Good. Notice that the average rate of change here is positive. So can you conclude that the population went up or the population went down based on the average rate of change? Up, right? Because the average rate of change is a positive thing. If the average rate of change was negative, the population would have gone down, which of course we can see from the numbers, but the rate of change also tells you that, right? Okay. What about the next one? What numbers are going to go in your numerator? Not everybody all at once. What number is going to go in the numerator? Good. And? Good. Okay, so the numerator is, we want to end in 2018, so we're using the output in 2018, the 4921. Started in 2014, so the output was 6288 there. What goes in the denominator? 4. Yeah, we're doing the 2018 minus the 2014, right? Notice that you want to make sure you have these matched up appropriately as well. The 2018 was the first number we wrote here. So the output associated with the 2018 should be right above it, right? Make sure you have the order correct. You don't want to flip-flop things since you're subtracting. Input's 2018. This is the output in 2018. Input is 2014. This is the output in 2014. That's okay? And what do you get when you simplify that? There are 41 point, would you 75. Okay. And again, this will be people per year. And the negative here is telling you that the population is going down, right? Yeah, the population is decreasing overall during that time period. So the population here was increasing over the time period. Average rate of change is positive. Negative over the time period. Decreasing over the time period. The average rate of change was negative. Is okay? Okay. Looking at part C, a little bit of a change here. It's asking what period of time was the population increasing, and basically this is reading it off the table. We talked about increasing before with a graph. This is just trying to do it increasing from a table. It's not going to be an exact thing, but we're going to do it with the information that we have. Remember, increasing meant as your inputs go up, the outputs also go up at the same time, right? So looking at the values in the table, what years can you say the population is increasing from where to where? 2002 to 2012, right? Just looking at the outputs in the table, here to here is bigger, 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 and now then it goes smaller, right? So 2002 to 2012, usually we use parentheses for our interval notation. Oops. For increasing. Does it, and I don't think it increases again after that, does it? Okay. So what can you say about decreasing then? What does it decrease? So it actually starts in 2012, right? It goes down, yep. So we would start and do 2012 to 2020. And that's why we don't use the little bracket on there, because it turned around at 2012 and went down. So again, we're looking at the years, looking for when the outputs go up. We went up from 2002 to 2012. And then starting in 2012, it dropped until we got to 2020. And that's all the information we have, so that's all that we can say. Questions on that one? It's okay? All right. All right, so I already defined what the average rate of change is for a function. I wrote that off to the side. So I'll just write it here again so you have the nice formula. I've got A's and B's rather than C's and D's. So in this case, using A and B, we would have f of B minus f of A over B minus A is your formula. So if you're given a function in function notation, should be able to do this with a straightforward application of your formula. So looking at this first example, we want the average rate of change of f of x is equal to 5x minus 3 from negative 1 to 4. So what are we going to do to compute that? What goes in your numerator? You don't have to actually plug it in yet. Just tell me what goes in the numerator according to the formula. Okay, so that's f of 4, right? Okay.
Then minus f1, or negative 1.
Good, f of negative 1, good. And then what goes in the denominator?
4.
So yeah, 4 minus the negative 1. Good, yeah, exactly right. So it's remember that from is where you're starting, the 2 is where you're ending, right? So you're doing either net change or average rate of change. It's where you ended up minus where you started. So it's going to be f of 4 minus f of negative 1, and then same order in the denominator. So what is f of 4 in this case? 17, because it's 5 times 4 minus 3. And what is f of negative 1? Good. 5 times negative 1 minus 3. And then 4 minus a minus 1 is 5 in the denominator. First set of parentheses there give me 17. And then minus a minus 8 over 5. $17 minus a minus 8 gives you 25, and we simplify and we get 5. Questions? Make sure you do keep track of your parentheses appropriately. Again, this says f of 4 minus f of negative 1. So I want to make sure I calculate my f of 4, calculate my f of negative 1, and subtract those two answers. Okay? Now, it's going to even be more important when we start doing these with constants that aren't necessarily named. So using letters rather than numbers. I want to make sure we have our parentheses in there appropriately so we have our signs correct. All right. Work on the next one for a minute or two, and then we'll chat about it. Ready to chat about it? Yeah, no, maybe. Yeah. Okay. All right. So again, we do an average rate of change. How do we compute it? In this example. Good. Good. All right. All right. So remember where you ended up, where you started, right? So where you ended up goes first. Where you where you ended up goes first. Where you started goes second. Outputs on top, inputs on bottom. Okay. All right. How do we calculate G of 5? Get 5 squared minus 2 times 5. That's our G of 5. Same idea, except with a 2 for the other one. And the denominator will be 3. Yeah. Okay. 5 squared is 25 minus 10, so I get 15 in the first one. 2 squared is 4. Minus 4 gives me 0. And if you simplify, you should get 5. Get the same thing we got in the last problem. What questions do you have? All right. So we've done, first example we did with a table. Next couple of examples we did with function notation. Another way that's a typical way to describe a function was with a graph. So here's one that has a graph. Another population idea. They give you the population in thousands in a city from 1970 to 2020. And then it asks you to calculate those different average rates of change. So see if you can do that real quick, and then we'll chat about it. See if you can interpret it from the graph. And then we'll have a chat. Feel free to talk to your neighbor, holler at Hope or me. Preferably Hope. No, just teasing. Did we at least get the first part done? What'd you get for the answer for the first part?
2000.
2000? Okay. So let's talk about why it's 2000. All right. So why is it 2000? Yeah. Okay. Yeah, go ahead.
You do 50 minus 40 because like 25 it starts there it's at 50 and 20 is at 40.
Good. So,
Divided by 5.
good. All right. So we're looking at those 2 points, right? When the x value is 20, the graph is up at 40. When the x value is 25, the graph's up at 50, right? So again, if you're doing it with the formula and we think of the function as p, we would have p of 25 minus p of 20 over 25 minus 20, right? Okay. The output at 25 is 50. The output at 20 is 40. So we get 10 over 5, which gives us 2. Now they tell you the population is in thousands, right? So the average rate of change is 2,000 units would be people per year. Does that make sense? And actually that second part is actually the interpretation. This, since we defined the P to be the output in thousands, this is actually the part that the answer they wanted for part A. Okay. That really was the 2. This is your interpretation. So what is it saying?
Increasing population by 2,000 people.
Yeah, good. So this just says is the population is increasing by 2,000 people each year. And that's an average, right? It's on average. Maybe sometimes it's increasing a little bit faster. Sometimes it's increasing a little bit slower. But overall, on average, it should be increasing to 2,000 people per year. Does that make sense? So again, converting it over to the thousands and then putting the units on it really is your interpretation, right? And since it's positive, it's going up by that much each year. All right. So let's look at the last part. Identify a period when the average rate of change is 0. All right. So let's go think about how average rate of change is defined again. Remember, it's that f of b, or f, whatever letters you want to use, f of b minus f of a over b minus a, right? It's a fraction, correct? When is a fraction equal to 0? Top and bottom are the same. It'll give you 1, right? Yep. Okay. Yes. So one of these pieces better be 0. Which is it, the numerator or the denominator? The numerator better be 0, right? If I put a 0 in the denominator, bad things happen, right? Okay. So the fraction will be 0 if the numerator is 0. So this problem is asking you what? It's basically asking you when this numerator is 0, what has to be true about these two values if the numerator is going to be 0? They better be the same, right? Right? So the average rate of change will be 0 if, so our average rate of change, is 0 if we end up where we started, right? If f of a and f of b are the same value. Okay. So let's go back, scroll back up here to the top and look at the graph. Erase those 2 little circles I put on there. Do you see spots where the outputs are the same? Yeah, I see lots of spots where the outputs are the same, right? In particular, and this is just one example, and I'm going to use that example because I put the dots on the graph. What's the output at this point? 40. The input's 20. The output's 40, right? What's the output here? Also 40, right? So there's 2 points where the outputs are the same, right? If the outputs are the same, then the average rate of change is going to be 0, right? So one interval would be
1990.
okay, is what, 1990 to 2010. This is x equal to 20. This is x equal to 40. Is that the only interval? No, there's lots of other intervals, right? If I scroll back up to the top again, any time that you've got a horizontal line that crosses in 2 points, you're going to get an interval where the average rate of change is 0, right? Maybe it'd be harder to read those off the graph. One part would be maybe this one here to here, right? Because I can read that a little bit better. So from 1970 to 2015, that'd be another one. That'd be a little bit easier to read off the graph. But anytime you've got a horizontal line that comes across and intersects in 2 points, that's going to tell you 2 places where the outputs are the same. The 2 places where the outputs are the same, average rate of change is 0. That's what that says. That makes sense? One of the reasons why we might care about such things, by the way, notice that I talk about doing these horizontal lines like this. Notice I go right to the top. There's a horizontal line that just basically touches the graph. That's also a spot where that graph has a maximum, right? That's an important concept in calculus. So it's one of the reasons why we care about when average rates of change are 0. Any questions on any part of that problem at all? All right. Speaking of calculus, the next concept is very important at the beginning of calculus, and it's the idea of the difference quotient. So I'm going to define what the difference quotient is, and then we're going to talk about what it really means graphically, if you will. All right? All right, so here's how you compute it. We take some other number, we call it h. We do f of a plus h. We do minus f of a on the top. And we divide it by h. I believe you were asked to do a homework problem on WebAssign that looked like computing that thing, right? Yeah. A little bit of a precursor to what we're doing here. We just said a second ago that what number can't we divide by? 0. So we want to make sure that the h might change, but we want to make sure that that h is not equal to 0. Why do we care? It's a good question. Why do we care? All right. So this difference quotient is the average rate of change of the function from x equal to x equal to a plus h. That's what we're doing, right? Notice that I'm going to put this in red. I'm not expecting you to write it back in the formula. Notice that on top, I could put a plus a, or not on top. In the denominator, I could put a plus a and a minus a. It didn't change anything, right? So notice this is my input. That's my output. This is my input. That's my output. That's why I can think of it as an average rate of change. Okay. Let's think about what this looks like graphically. All right, so let's say I have some function. I'm just going to draw some random picture here. Nothing special about what I drew, okay? Let's say my a is right here, and then I'm going to do a plus h is over here. I'm taking a, and I'm adding a little bit. Maybe h is negative, and I'm subtracting a little bit. That's all the h is just representing is I moved a little bit to the right, or I moved a little bit to the left. When we put these 2 points in here, this would be the point a plus h, f of a plus h. This would be the point a, f of a. Remember, that's how we graph functions, right? You put in the input, you get out the output, you plot the point, right? Do you agree? That's how we get the points? Okay. We connect the dots there with a red line. You remember how to compute slope of a line? The y equals m was supposed to be the equation, one of the equations, the form of an equation of a line, because I wanted to figure out the m part, the slope. How do we figure out the slope part? This is something we're going to talk about next week too. Remember how we do slope?
Is it y2 minus y1 over x2 minus x2?
Yeah, it's that rise over run idea, right? How far up or down do you go, and then how long it took, right? So if I wanted the slope of this line, the slope here would be what? Your slope is, we'll call it rise over run, right? You would do the difference of your y coordinates over the difference of your x coordinates. Notice that is that difference quotient. So the difference quotient is a slope, is what it is. The difference quotient, it's the slope of the line through those 2 points. A f of a and a plus h, f of a plus h. I told you a minute ago about the average rate of change being 0 and kind of sliding it up closer and closer to that maximum. I'm talking about it just touching there. Slope of a horizontal line is 0, right? Okay. So this quantity that we're talking about here is, it helps us later on in calculus to be able to talk about where those functions might have that horizontal line that just goes and touches the top of a graph or just touches the bottom of a graph. Okay. That's why we care about this particular quantity. It gives us a way to measure change of a function. That's the idea. Okay? All we're going to do is use it for some computations. We're not going to do a lot with it besides that, but it does have important relevance in calculus. Lots of important relevance in calculus. Yes?
On that second one, why did the a plus h minus a turn into just h?
I have a minus a.
Okay.
Yep. Yep. All right. So let's do a couple of examples with these. They do some nice algebra play, if you will. All right. So first one here, do a straightforward idea here. We've got f of x equals 5x minus 3. We want to do the difference quotient at a. All right. So we want to do f of a plus h minus f of a all over h. And this is what I was just mentioning a little bit ago. Make sure that you do your parentheses appropriately. Now I'm going to use brackets just to kind of even set it off more. Remember what the function notation means? You take out the x and you literally put in what's inside the parentheses for your function notation in for that x. Okay? This does not mean just take h and add it to the end. Okay? This means take out the x, put in a plus h for the x. So here's f of a plus h, here's f of a. But I need to make sure I have parentheses around each of these things because I'm going to subtract this whole thing, right? Okay. It's important to keep track of your grouping symbols. You want to make sure you have your signs all correct. So now let's simplify. Distribute the 5 through. So we'll have 5 times a plus 5 times h minus 3. Distribute the minus sign through. I get a minus 5a plus a 3. Anything nice happen in your numerator? The 5a? and the 3 both cancel out, right? So all we're left with is 5h over h. What can we do now? I divide out the h's, right? And we get 5. So we get a specific number in this case. We do need to be a little bit careful. What number, starting off this problem, what number can you not plug in for h? 0, right? So at the very, very end, we want to say that our h is not equal to 0. By the way, I talked about lines a minute ago. This looks like your y equals mx plus b form, doesn't it? The m is the slope. What's the slope of that line? 5. What answer did we just get for the average rate of change or the difference quotient? 5. What did I tell you the difference quotient gave you? Slope. Ooh, hey, not a big surprise. We got the same answer for slope. Okay. All right. Let's do it for a different function here. For our g here, that's 1 over x. Again, the difference quotient is this very specific definition. G of a plus h minus g of a all over h. What is g of a plus h? What do you have? The x, yeah, the g of x is 1 over x, so g of a plus h is... Again, what do you do with these? What do you do with what's in the parentheses? Plug it in for x. So what is g of a plus h? 1 over a plus h. Good. What's g of a? 1 over a all over h. All right. So now we want to simplify. Our goal in any time that you want to simplify something with a difference quotient is to kill the h. If you see wicked, it sounds like kill the witch. Kill the h. Okay? Okay? Kill the h. That's the idea behind this. We want to make the h go away in the denominator. All right? To be able to notice in the previous one, everything canceled out nicely to do that, right? And then we were able to cancel out the h's. Okay? This one, not so nice, but I do have a complex fraction here, so I need to simplify the numerator and get a common denominator. What will your common denominator be for the numerator? I got an a plus h and an a, right? So I need them both. Okay? So I need to multiply the first fraction by a over a, and I need to multiply the second fraction by a plus h over a plus h. Think about if you just had fractions, right? If I want to do 1/3 plus 1/4, what do I need to multiply the first fraction by? To get a common denominator, I need to multiply the first one by that one's denominator, 4, and this one I need to multiply by 3. That one's denominator, right? That's basically all I did here. Okay. The reason why we get a common denominator is it allows us to combine the fractions on top. So I have a minus the whole thing, the a plus h. So I said the parentheses are important. A minus the quantity a plus h over our common denominator. And then still all over h. That's still on bottom. In the numerator, how does the numerator simplify? The numerator of the numerator. How does the numerator of the numerator simplify? This part right, I'm talking about this part right here. What does that simplify to? So it's a minus h, right? So what happens with the a's? They cancel. So we just get negative h. You got to make sure we distribute the minus sign all the way through, right? Now, well, I told you our whole goal is to do what? Get rid of the h, right? I've got to still have a complex fraction, but I can think of this as h over 1, right? What do you do when you divide by a fraction? You multiply by the reciprocal. Now do your h's go away? They cancel each other out, don't they? So we have negative 1 over a times a plus h. And again, with the caveat that h is not 0. One was a little bit more complicated, right? You get that common denominator and do some simplifying. A little bit more complicated. Let's do one more example here before we have the last 3 minutes here. Where we got this last one. Oh, I used a h for the function name. That's a bad idea. Let me change this function name to f. I'm just going to cross that out. Calling that h. There's going to be two things that mean h. I don't want that to happen. Let me just call it f. So f of a plus h minus f of a all over h. Again, remember, this means to do what again? What do I do with this a plus h? Plug it in for x. It does not say just stick a plus h on the end. Okay? So we would have the quantity a plus h squared plus 2 times a plus h minus 3. Okay? Take out the x and put in a plus h. I got to do the same thing for the next one, but I'm just putting an a in, right? So we'll have a squared plus 2a minus 3. Basically, x is like a hole to fill. I'm filling it with a plus h in the first case, filling it with a in the second case. I want to simplify the top. What do you think we want to do with each of these things here? What do you think I want to do with the a plus h? Multiply it out, right? Remember, you cannot just distribute the exponent, right? You've actually got to FOIL it, distribute everything. What do you get when you FOIL out that part? Yep. Plus an AH, yep. Yep. Good. Right? Because I remember a plus h squared is a plus h times a plus h, right? You got to do a times a times h times a, h times h, right? Distribute your 2 through, you get 2a plus 2h minus a 3. And then I need to distribute the minus sign through in the second case. So it'll flip all those, oops, that's a minus 2a. It'll flip all those signs in the middle, or on the second piece, I mean. Do you see anything that goes away? A squared goes away. Anything else? 2a goes away. Anything else? 3 goes away. Notice everything else that's left has what in it? An h. What did we say our goal was? Get rid of the h in the denominator, right? Everything on top has an h in it, means we can factor out an h. This has to happen when you do this, by the way. Okay? If you do one like this and you don't get all the terms that don't have an h to cancel, you've done something wrong. Okay? I need to get to a point where I can factor out an h. When I factor out an h, this one I'm left with 2a's, right? So I'll have a 2a. Factor out an h out of the h squared, I just have one h left. Factor out of this one, I have a 2 left. And now the very, very last step to do is to cancel the h. So we get 2a plus h. Oops, I forgot my. No, I'm okay. 2a plus h plus 2. I thought I forgot something, but I didn't. My brain was wrong with where the 2 was. And again, that little caveat at the end that h can't be 0. All right. If you want to practice that last one for over the weekend, you'll need to multiply by the conjugate. So if you remember what a conjugate is. So we'll talk about that next time, as well as get into new stuff. All right. So have a good weekend, everybody. We'll see you on Monday.